subduction zone. It's the subduction zone located east of New Zealand's North Island, where the Pacific Plate is subducting beneath the Australian plate. And the Pacific Plate in this area is thicker than normal oceanic lithosphere because it includes the Hikurangi Plateau, which is a large igneous province emplaced around 120 million years ago. And as with Cascadia and Alaska, there are long strike variations in the properties of the Hikurangi subduction zone. So for instance, there's an observable change in the exposure of seamounts on the incoming plate, with more rough seafloor apparent in the northern part of this margin than in the south. And you can see that very clearly in this seismic reflection profile from the northern part of the margin, where there is this large seamount on the incoming plate, and then this feature beneath the fork, which is generally accepted to be a subducting seamount. One of the most important along strike variations at Hikurangi is the change in interseismic coupling, which increases as you go from north to south along this margin. And you can see that by the red colors that represent higher coupling coefficients in the south, and the bluer colors which have lower coupling coefficients in the north. So this is essentially telling us to expect that the plane interface in the south is more locked, and the plate interface in the north is creeping or slipping more aseismically. So somewhat related to this interseismic coupling variation is the along strike change in slow slip event occurrence. And the map on the left here shows cumulative slip patches since 2002 in purple. And you can see that these slow slip events are happening more shallowly in the north because they're closer to the trench, and then they get deeper as you go to the south. And they also occur more frequently in the north. So of course, we have a long way to go in our understanding about these slow slip events. But as Noah alluded to yesterday, some research suggests that fluids are a key player in slow slip. And so this was a driving motivator for using electromagnetic techniques to investigate these along strike patterns further. So I'm sure since Samra is there, he's been very vocal about why EM is a powerful and useful tool, but I'm gonna try to help indoctrinate you a little bit more. And this figure kind of helps explain why EM or electromagnetics are such a great and useful method for when you're trying to estimate the amount of fluids in crustal rock. As EM geophysicists, we're interested in measuring the electrical resistivity or its reciprocal electrical conductivity, and we go back and forth between saying resistive and conductive a lot. So just remember, things that are more resistive are going to be less conductive and vice versa. If we look at this figure, we can see resistivity spans 5 orders of magnitude for some of these common earth materials of interest in the marine environment. And that's useful for when you're trying to tease apart the cause of different resistivity anomalies in your models. If we look in particular at the oceanic crust, we see that its resistivity is mainly controlled by its porosity. And that, of course, is because seawater is so much more conductive than non-porous oceanic crust. And the same can be said about marine sediments. This fact is what allows us to infer the porosity of the crust and seafloor sediments from knowing their resistivity. I'm not going to go into the methodology here, except to say that we collected both the active controlled source electromagnetic or CSEM data and the passive source magnetotelluric or MT data for this project. And the models that I'm going to show incorporated both of those data types. So this is a map of our Hikurangi Trench Regional Electromagnetic Survey to image the subduction thrust, which was work that we carried out just over 3 years ago at this point. We gathered CSEM and MT data in these 3 trench crossing profiles and 1 trench parallel profile shown here in orange circles. And these 3 trench crossing profiles were co-located with multi-channel seismic reflection data, and those are the ones I'm going to be talking more about today. We also collected these 42 receivers for long period MT in order to look at the deeper structure of this margin. And GNS Science New Zealand, in addition to our offshore data, had collected all of these green circles of onshore land MT data. So taken together, we just have this very large amphibious array of electromagnetic data to work with. Now, looking at all 3 of the final resistivity models from those trench crossing profiles, Here I'm showing you resistivity as a function of depth and distance from the trench, where the trench is denoted by this dashed black line. Resistivity is in ohm meters, with blues being more resistive and the reds being more conductive. And so looking at all three of these profiles together, I think it's clear that the resistivity is becoming more and more heterogeneous as you go from south to north along this margin. And it's really always interesting to me to look at all three and just to realize and recognize that this is one subduction zone, and yet we have three vastly different resistivity profiles coming from it. So we're going to zoom in on the northern profile first. Myself and my co-authors published a paper on this line last year in Nature. So if you're interested in more details and to look at more figures than I'll have time to show today, please do check that out. So this map to the right is showing the locations where data have been collected and seismic activity has been documented in this area. And it's by no means comprehensive, but it's pointing out some of the key things that I'll mention later on in the talk. So first up, of course, these gray squares are EM receivers. There were also 4 IODP drill sites along this profile in red dots here. And then there's all this evidence for fluid seeps in these cyan squares. These orange contours are the slow slip contours from the 2014 slow slip event that occurred in this region. And these white stars here are the repeating earthquakes associated with that slow slip event. There's also this blue star, which is the approximate epicenter of the 1947 tsunami earthquake. And you'll notice on the incoming plate, there's this very large seamount called Turanganui Knoll. And there's also this white outline in the forearc, which designates a contour, a depth contour from that subducting seamount from magnetic inversion. So let's look again at the resistivity model for the incoming plate and the forearc in turn. Here again is the incoming plate's resistivity. Here, the resistivity is dominated again by this seamount, Turanganui Knoll, and by the Hikurangi Trough. And Turanganui Knoll is actually morphologically more similar to a geo, which is a flat-topped seamount, except you can see it's no longer flat-topped, and that's probably because of later stage volcanism that emplaced these cones on top of the knoll. So what stands out to me when I look at this Turanganui Knoll is just how complex the resistivity structure is. So it's in no way a homogeneous feature. Then Hikurangi Trough is, it contains siliciclastic and pelagic sequences. And in the north, those are about 1.5 kilometers thick. And underneath those sequences, there are some buried volcanic cones, which I didn't outline here, but they're more of these green features in resistivity space. So since this is the first very high resolution electromagnetic image of a seamount, I am going to point out several of the important features that we noticed in it, starting with this resistive part of the seamount that I'll call the resistive core of the seamount, or R1P. Because this is so resistive, we know that it's going to have a low porosity, and we interpret R1P to be a core of intrusive material like gabbros that's cooled slowly. Next is this conductive tongue of material, C2P, that cuts into the resistive core, and it coincides with the seismically imaged normal fault. Additionally, because there are heat flow data that were collected along this transect, we can see that the heat flow values decrease upon approaching this fault. And that suggests that the fault is a conduit for fluids from hydrothermal recharge. The heat flow values also increase above one of the cones, and that suggests to us that this entire seamount is actively participating in some level of hydrothermal recharge and discharge. So the next feature to note is this conductive matrix of material, C1P, that sits on top of the resistive core. Because it's more conductive than the core, we know automatically that it's going to have a higher porosity than R1P. And if we think about how seamounts form, that gives us an idea that C1P is likely a combination of extrusives and volcaniclastics and probably some altered mineral phases from hydrothermal activity. And then finally, on top of the knoll is this resistive cap, R2P. Because it's resistive, we know it's going to have a lower porosity than C1P. And thinking back to when this feature was a geo, our interpretation for R2P is that the seamount was building and building and building until it breached the surface of sea level. And then the igneous material that was building it was not coming into contact with cold seawater, but was instead allowed to cool slowly and maintain that low porosity. So before modeling the EM data, I definitely wasn't expecting the seamount to have this quite of a complex resistivity structure. And maybe I should have given how seamounts form, but I think I had definitely gotten accustomed to treating seamounts like materially and mechanically uniform features. And this work has just reminded me that that is not the case, especially when we consider how much water these seamounts can be carrying. So using Archie's law, I converted the resistivity model into a porosity model, which is shown here. And looking at the porosity of C1P and C2P, we can see that this seamount is quite porous for oceanic crust. And in fact, if we look at some porosity estimates from drill cores into oceanic crust at the Mid-Atlantic Ridge and the East Pacific Rise, we see that in the upper 1 kilometer of this core, porosity decreases down to 2%. But I estimate that the upper 3 kilometers of Turanganui Knoll has an average porosity of 9 to 13%, which is way more porous than average oceanic crust. Doing a more direct comparison in terms of the techniques, I also looked at the porosity of unfaulted abyssal plain crust off the Middle America Trench from CSEM data. And I estimate that Turanganui Knoll will carry 3 to 5 times more water to the subduction zone than normal unfaulted oceanic crust. So this result is really exciting because it implies that seamounts can locally transport with them a relatively large amount of water to subduction zones. And that, of course, is going to have implications for any of the forearc processes that involve water, like slow slip. So let's again go back into this forearc. Here we see a very heterogeneous forearc. Like we saw when all 3 profiles were together, this is the most heterogeneous forearc of the 3. There appear to be these 3 conductors embedded in a more resistive background. And based on the active thrust faults in this region and how they bound some parts of the conductors, and also based on the prevalence of fluid seeps in this region, it's possible that in some of these cases we're imaging fluid pathways. It's also very possible that C3F is a mass of underplated sediments. And I'm plotting the projection of the 1947 tsunami earthquake on this profile so you can see how close it plots to C3F. So it's been hypothesized that low rigidity material in an accretionary wedge can help tsunami generation. And so it's very plausible that C3F could be a mass of underplated sediments. And that could also be the explanation for what C1F and C2F are, but I would argue for a different interpretation related to this feature on the subducting slab, which I'm calling R1F. So we interpret this cone of very high resistivity material as the resistive core of the subducting seamount. And it's kind of around the same location as the seismic reflection interpretation of where the subducting seamount is, and also where the magnetic basement is. And a more recent result from Arai-san and others used 3D tomography to show that there's this high velocity feature shown in dashed purple here that's located around the same area as R1F. And it also has a similar shape to R1F. So that gives us more confidence that R1F is the core of a subducting seamount. So based on the relative positions of R1F to these 2 landwardmost conductors, I'd argue that the conductors are related to enhancement of porosity from damage associated with this subducting seamount. And I would say that is especially true of C2F. And to support that claim, I'm going to show you where the relocated seismicity from these September to October 2014 slow slip event plots on this profile. So for those of you who haven't seen this yet, it's going to be really exciting. And even I, who've seen it many times, still find this exciting because amazingly, a lot of this seismicity is clustering in and around C2F. So we think that this is the closest thing to in situ evidence that is directly connecting the effect of this upper plate damage from subducting topography to the generation of highly porous zones in the forearc that are linked to slow slip events. And I'm going to leave that here for now so we can move on to the central profile. So this profile, pictured here again, was chosen so that it'd be around the region that transitions from strong plate coupling in the south to weak plate coupling and shallow slow slip events in the north. You can also see, if you look at the northern and the southern profiles, that this profile is mainly forearc because the forearc is very wide in the central part of this margin. So there won't be a lot of incoming plate on this particular profile. Here again is the resistivity model for this profile. The slab is down here as this dipping resistive feature at depth. And compared to the northern profile, the resistivity of the incoming plate and the forearc, as I said before, is much simpler. We also don't see any evidence for large seamounts in this profile. Now, it's really helpful to look at the resistivity model with co-located seismic reflection data on top. And luckily, Andrew Gase has been very willing to share his data ahead of publication. And so he shared that with me, and you can see them together here. I've put the 2.7 and 10 ohm meter contour on the resistivity just to help guide your eye in finding the resistivity gradients. And then these red circles are Andrew's picks for the top of the subducting Hikurangi plateau. Now, there are a lot of shallow forearc resistors in this profile. And based on where the BSR is, and based on where these resistors are, it's likely that these are showing us the presence of free gas or gas hydrate. And that tracks pretty well with other work that's been done at this margin, which shows an abundance of gas. Looking towards the landward side of the profile on the left here, we do see this upward slope in the resistivity that follows the same slope in high reflectivity. And that's interpreted to be a part of the forearc Mesozoic basement. So it's not the slab doing something weird where it's like trying to accrete or something. This is just part of the upper plate. Again, we see some anomalously high connectivity patches in this forearc. And some of them are bounded by faults. And in fact, some of the thrust faults seem like they are separating higher connectivity from higher resistivity, which is interesting. Maybe these conductors are related to rough subducting topography or small seamounts. They could also, again, be indications of underplated sediments. But one thing that's really interesting is that some of the patches of anomalously high connectivity seem to coincide with breaks in what Andrew has identified as these high reflectivity zones, or HRZs. So we're still thinking about the reasons why this is the case. But one possible explanation is that it indicates heterogeneous fluid distribution at the plate interface. So today, again, we've got our heterogeneities that we don't quite understand. Okay, so finally, along the southern Hikurangi margin, we can see right away from the bathymetry that there are no exposed seamounts here. And in fact, the sediment cover in this part of the margin is much thicker than in the northern and central parts of the margin. So here again is the preferred resistivity model for the south. And if we use this 10 ohm meter contour as the approximate base of the sediments, then we can see that sediment on the incoming plate here is at least 4 kilometers thick, whereas it was only 1.5 kilometers thick in the north. As I've said before, this is the simplest of the profiles in terms of resistivity. So I did a very basic depth migration on the unit boundaries and faults from available seismic reflection data and estimated where the base of the gas hydrate stability zone would be. That's this BGHSC, shown as this dotted gray line. And again, in this southern transect, we see there are shallow forearc resistors, R1 and R2. And because of where they're located around the BGHSC, it's likely that they are more free gas or gas hydrate. There are also some deeper resistive anomalies in this profile, R3 and R4. And because they're below the BGHSC, maybe they're free gas, but looking at how especially R3 is making up the footwall of a thrust fault, it's possible that they are instead showing us where dewatering has occurred and might be suggesting that this is a well. So to conclude with the EM portion of this, I'll just reiterate that the resistivity structure of the Hikurangi margin varies along its strike, which seems to be related to changes in sediment thickness and the exposure of seafloor topography on the incoming plate. And please remember that seamounts are like sponges, so they can carry a lot of water with them to subduction zones, and that's going to be important for slip along the plate interface. Okay, in the little bit of time I have left, I just want to talk about some of the really great published and unpublished work that has been done in the past year on this margin. And I obviously can't get through all of it, but some of these studies that I've pulled out are very relevant to the goals of this workshop. So first off, from this seismic attenuation study by Jenny Nakai and others in the northern Hikurangi margin, the authors found these zones of high attenuation in the same locations as high VPVS ratios and high reflectivity zones. So the high attenuation here is shown in orange from these 3 different transects, and this is QP and QFS. So all of this suggested to the authors that overpressurized fluids at the plate interface are linked to shallow slow slip. In this work led by Srisharan Sridharan, the authors measured the frictional strength, stability, and healing behavior of carbonates and smectite-rich volcaniclastics taken from this IODP core into the Hikurangi trough. And they found that frictional velocity dependence and critical slip distance increased with fault slip rate. And then the figures to the left show that they also found low healing rates in the volcaniclastics, meaning that that material can't store strain energy over long time scales. And they found higher healing rates in the carbonates. So the authors suggest that it's this mixture of conditionally stable volcaniclastics with the frictionally stable carbonates that could be a really important contributor to shallow slow slip. By doing some full waveform inversion analysis from seismic data collected at the southern limit of the shallow slow slip area, Ozyanonov and others estimated the elastic properties and the pore pressure along this profile. And then they used the results in some rate and state friction models. So among other things from the study, they found that the megathrust fault has these marked variations in pore pressure and elastic and also maybe frictional properties. So you can see kind of that being shown here and here. And then from the rate and state friction models, this suggests that the rocks at the plate interface should be approximately velocity neutral in order to generate shallow slow slip. Andrew Gase sent me this slide from multi-channel seismic data in the Shire project. And it's showing to the left the locked part of the margin, and to the right there's this map of sediment thickness where the reds are thinner sediments and the blues and greens are thicker sediments. So what he has observed is a contrast between deeply subducting sediments in the south and seamount collisions in the north, and that aligns well with the coupling transition. And then finally, Dan Bassett and others recently published this P-wave velocity model from some wide angle MCS data collected along the entire Hikurangi margin. And they show that the wave speeds in the forearc decrease from north to south, and that decrease is occurring right around where you have the transition from locking to creeping. So they interpret this very marked difference in wave speed as being caused by the extent of the Torles basement unit in the upper plate. And the major takeaway from this study is that geological architecture of the overriding plate may be a key factor in determining that up-dip limit of stable versus unstable versus conditionally stable fault slip. So I'm going to leave you with a few answers to the questions that I posed earlier, and just kind of echo what people have been saying, that I think in order to fully answer these questions, if these questions can fully be answered, I think we're going to need to continue gathering co-located data and really collaborating to integrate the results from those different data sets. So thank you. I don't know if there's time for questions or not.
And Mānoa, can you come? Yeah, maybe we need to move on, but while Ammonia is preparing for the next talk, I can take a quick short questions.
I have a question for you, Christine. This is Kaylee Condit. Hopefully you can hear me. Hi, that was a great talk. I love seeing your stuff every time. I wanted to know how ubiquitous you think like subducting seamounts are at other subduction zones, and do you think in other places they're also bringing down a lot of water?
That's a great question, Kaylee, and it's one that I am still thinking about and hoping maybe to get some funding to answer more. But I think that some of the factors we probably need to consider when we're thinking about how much water seamounts can subduct is their size. I think as you get larger seamounts, you'll have a higher percentage of them that seamount that is extrusives versus intrusives. So that's definitely going to contribute to how much water they can carry. In terms of ubiquity, if you want to call, like, it depends on what you want to call a seamount, but any type of seafloor topography is going to be, I think, quite ubiquitous in a marine setting. And we'll have different levels of height. So there's lots of volcanic cones all over the Hikurangi Margin. Some of them are buried now, but this is likely true in other parts of the world as well. And you've got, ridge subduction, you've got geosubduction. So I think it happens in a lot of places. How much water is subducted depends on the size.
Great, thank you.
All right, let's move on.